Good evening, and welcome to the Sleepless Curiosity. Here is a number that should stop you before you even get comfortable. 6,000. That is how many worlds beyond our own solar system humanity has confirmed since 1992, patiently, one faint signal at a time. And out of all 6,000 of them, this is the sharpest photograph our species has ever managed to take of one. A single trembling smudge of light. No oceans, no coastlines, no mountain ranges catching a distant sunrise. Just a dot and a question that has followed you since the first night you ever looked up and wondered if anyone up there was looking back. Here is what almost no one knows. Sitting inside NASA right now, quietly funded, quietly tested, is a real plan, grounded in real physics, to solve this. Not with a bigger mirror, with something stranger. A plan to turn our own sun into a telescope 90 kilometers wide, built on an idea Albert Einstein once looked at and said, "This will never actually be observed." He was wrong. And if the people working on this are right, you could be alive on the night humanity finally sees another world in real, breathing detail. Get comfortable. Settle in. And if this is your first night here, hit subscribe, because tonight we go looking for someone else's sky. Now let's slowly ease into this. Part 1. The dot that was never going to be enough. In 1992, two astronomers pointed their instruments at a dead star, a pulsar, the collapsed corpse of something that had once burned as a sun, and found something that should not have been there. Tiny rhythmic irregularities in the timing of its radio pulses. Something was tugging on it, something small, dark, and orbiting. It took months of careful, skeptical checking before anyone was willing to say the word out loud. A planet. Not one of the 8 we already knew intimately. Not one of the worlds our own solar system had raised us on, but a planet circling another star entirely. The first confirmed exoplanet in human history, discovered not by seeing it, but by feeling its gravity ripple through the light of something else. That discovery cracked something open. For all of recorded history, human beings had looked up and simply assumed, without proof, that other worlds existed out there, scattered among the stars like grains of sand on some infinite beach we would never walk. Poets had guessed at it. Philosophers had argued about it. But nobody had ever confirmed it. And then, in the space of a single announcement, the universe stopped being a philosophical question and became a research subject. What followed was one of the most productive scientific manhunts in the history of astronomy. Astronomers built 2 primary tools to keep finding these worlds, and it is worth understanding both of them properly, because everything else in tonight's story depends on grasping just how indirect, how second-hand our knowledge of these planets has always been. The first method is called the radial velocity technique, though you may have heard it described more simply as the wobble method. Here is the picture. You assume, incorrectly but usefully, that a star sits motionless while a planet orbits around it. In reality, both bodies orbit a shared center of mass, a balance point between them. If the planet is small and the star is large, that balance point sits very close to the star's own center, but it is never exactly at the center, which means the star itself traces out a small, slow, almost imperceptible loop in space, tugged gently back and forth by the gravity of the planet orbiting it. As the star wobbles toward us and away from us, the light it emits shifts. Toward us, the wavelengths compress slightly, shifting blue. Away from us, they stretch, shifting red. This is the same Doppler effect that changes the pitch of an ambulance siren as it passes you on the street. Astronomers learned to detect that flickering shift in starlight, tiny fractions of a nanometer, and from it, infer the presence, the mass, and the orbital period of a planet they could not see at all. The second method is even more elegant in its simplicity, and it is called the transit method. If a planet's orbit happens to be aligned just right so that from our vantage point here on Earth it passes directly in front of its star, then for a few hours that star will dim. Not by much. An Earth-sized planet crossing in front of a Sun-sized star dims that star's light by roughly 1/100th of 1%. It is the equivalent of watching a stadium floodlight from miles away and trying to notice when a mosquito flies in front of it. But telescopes built specifically for this purpose, most famously the Kepler Space Telescope, learnt to watch hundreds of thousands of stars simultaneously, waiting patiently for that flicker, that infinitesimal dimming, over and over again, at a regular rhythmic interval that could only mean one thing. Something was orbiting. Something was blocking the light on a schedule. Between these two techniques, the wobble and the dimming, humanity built an entire census of the galaxy's planets without ever directly seeing a single one of them. Think about the strangeness of that for a moment. Nearly all of our knowledge about 6,000 other worlds comes not from looking at them, but from watching the behavior of the stars they orbit and mathematically reconstructing what must be out there to explain it. It is a little like knowing there is a person in a dark room, not because you can see them, but because you can hear the floorboards creak in a pattern too regular to be nothing. Naturally, the next ambition was obvious. If we know they are there, can we actually see them? Can we point a telescope, a real one, at a distant star system and simply take a photograph the way you would photograph a mountain range or a coastline? By the early 2000s, the answer was a very tentative yes, but only under the most forgiving circumstances imaginable. The first directly imaged exoplanets were enormous, young gas giants, many times the mass of Jupiter, still glowing faintly with the residual heat of their own formation, orbiting their stars at vast distances, far enough out that a telescope's coronagraph, a device built to physically block the glare of the central star, had a fighting chance of revealing the planet hiding in the darkness beside it. But even these images, even the best of them, were nothing more than single pixels of light. A dot. A firefly caught for a fraction of a second at the edge of a photograph. And here is the part that should genuinely humble you. Those triumphant early images, the ones that made headlines around the world, were of the easiest possible targets. Massive planets, hugely far from their stars, still radiating their own primordial heat like dying embers. An Earth-like world, small, rocky, cool, reflecting only a faint fraction of its star's light rather than glowing on its own, is a categorically harder problem. It is not just a smaller target, it is a different kind of target entirely. To understand why, you have to sit with two brutal numbers. The first is the sheer angular size of the problem. To resolve real surface detail on a planet as small as Earth, sitting some 4 light-years away at the nearest possible star system, you would need a telescope mirror roughly 90 kilometers across. For comparison, the James Webb Space Telescope, the most sophisticated instrument our species has ever placed in orbit, carries a mirror 6.5 meters wide. To go from 6.5 meters to 90 kilometers is not an engineering challenge you solve by building a slightly bigger version of what you already have. It is a leap of roughly 14,000 times in scale. No material we know how to manufacture, no gantry we know how to construct, no rocket we know how to build could ever loft something like that into space in one peace. And even if you somehow solved that problem, even if some future civilization found a way to assemble a mirror the size of a small country floating in orbit, you would run headfirst into the second number, and this one is worse. The contrast problem. An Earth-like planet, reflecting sunlight rather than generating its own, is roughly 10 billion times fainter than the star it orbits. 10 billion. Not 10,000, not 10 million. 10 billion. It is the visual equivalent of trying to photograph a single firefly hovering directly beside a floodlit football stadium from a vantage point hundreds of miles away, while the stadium lights are blazing at full power and the firefly's glow is a fraction of a single lumen. We do have technology built specifically to fight this problem. Coronagraphs, precision-engineered masks and optical tricks that physically suppress the light of a central star, allowing faint objects nearby to become visible. And they work. They have found planets, faint disks of dust, hints of structure around nearby stars. But the very best coronagraphs humanity has ever built can suppress starlight by a factor of roughly 1 million. We need a factor of 10 billion. Do the arithmetic, and you find our very best technology is still 10,000 times too weak for the job. Not close, not almost there. Off by 4 orders of magnitude, staring at a wall that conventional optics simply cannot climb. So here is where the field stood for decades. We knew with total confidence that thousands of other worlds existed. We had their masses. We had their orbital periods. We had rough guesses at their atmospheres, pieced together from the barest flickers of light passing through them during a transit. But we had never seen one. Not really. Not the way you have seen a photograph of the Grand Canyon, or the way astronauts have seen the blue curve of Earth's own horizon from orbit. Every exoplanet in the known universe remained, in the most literal sense, unseen. And it would have stayed that way, quietly filed under problems too large for the physics we had, if not for a strange and almost accidental idea that had been sitting patiently in the scientific literature since the early 20th century, buried in the margins of a theory nobody thought had anything to do with photographing distant worlds at all. Part 2. The lens Einstein didn't want to build. In 1915, a German physicist working largely in isolation from the chaos of the First World War finished a theory that would eventually rewrite what gravity even meant. Albert Einstein's general theory of relativity proposed something that, on its surface, sounds almost too simple to be revolutionary. Gravity is not a force reaching invisibly across empty space, pulling one object toward another the way Newton had imagined it for over 2 centuries. Gravity is geometry. Mass and energy bend the fabric of space and time itself, warping it the way a heavy ball placed on a stretched sheet of fabric warps the sheet around it. And anything moving through that warped space, including light itself, has no choice but to follow the curve. That last part is the one that mattered most for tonight's story. Light bends. Not because light has mass and gravity is tugging on it in the old Newtonian sense, but because the space light is travelling through has itself been curved by whatever massive object sits nearby. Einstein's equations predicted this precisely, down to a specific calculable angle, and in 1919, an eclipse expedition led by the astronomer Arthur Eddington confirmed it, watching starlight bend exactly as predicted as it grazed past the edge of the sun during a total eclipse. It was one of the great triumphant proofs in the history of science, and it made Einstein, almost overnight, the most famous scientist alive. But there was a stranger, quieter implication buried inside that same idea, one that Einstein himself seemed reluctant to take seriously. If a massive object like a star can bend the path of light passing near it, then in principle, that star could act like a lens. Not a lens shaped from glass, ground and polished by human hands, but a lens made of curved space itself, focusing and magnifying the light of anything positioned on the far side of it. The man who pushed Einstein to actually confront this idea was not a professor, not a colleague at a prestigious institution, but a Czech immigrant named Rudy Mandl, working as a dishwasher in Washington, D.C. Mandl had no formal physics training, but he had an idea that would not leave him alone, and in the mid-1930s he travelled to Princeton with the singular goal of getting Albert Einstein to listen to him. He believed that gravity could magnify starlight the way a magnifying glass magnifies the sun, focusing distant light into something brighter and clearer than it would otherwise be. Einstein was not impressed. He considered the idea, ran through the mathematics almost dismissively, and told Mandl it would never actually be observed in practice. The alignments required, he believed, were simply too rare, too precise, too astronomically improbable for anyone to ever stumble across a real example of it in the sky. But Mandl would not let it go. He kept writing. He kept following up. And eventually, somewhat reluctantly, Einstein agreed to formalize the concept into a short paper and send it off for publication. What Einstein wrote in a private letter accompanying that paper is one of the more quietly cutting lines in the history of physics correspondence. He described the work as being of little value, but noted that publishing it would make, in his words, the poor guy happy. He closed the paper itself with a line that reads almost like a dismissal carved into stone. There was, he wrote, no hope of ever observing this phenomenon directly. He was wrong. Decades after Einstein's death, astronomers pointed increasingly powerful telescopes at deep space and began finding exactly what he had declared unobservable. Massive galaxies and galaxy clusters sitting directly between Earth and far more distant galaxies behind them were bending and magnifying that background light into strange, beautiful arcs and rings. When the alignment was close to perfect, the distorted image would form a complete circle of light wrapped around the foreground galaxy, a phenomenon that astronomers now simply call an Einstein ring, a small, quiet correction to a man who had once been certain the effect would never be seen. And then, in 1979, a scientist named von R. Eschleman took the idea somewhere Einstein himself had never imagined. Eschleman was not thinking about distant galaxies or cosmological surveys. He was thinking about our own sun, sitting at the centre of our own solar system, and whether it too could act as a gravitational lens. If it could, he reasoned, it might be possible to use that lensing effect not just to observe the universe, but to communicate across it, sending or receiving signals amplified by the sun's own gravity, reaching across distances that would otherwise be impossibly faint to detect. It was a strange, almost science-fictional proposal for its time, published quietly, discussed in specialist circles, and then largely left alone for decades, because the technology required to actually test it did not yet exist and would not exist for a very long time. But the physics underneath the idea was sound, and it is worth walking through it slowly, because understanding exactly how this works is the key to understanding everything that follows tonight. Picture light leaving a distant planet, travelling outward in every direction, the way light always does. Most of those photons head off into empty space and are lost forever. But some of them happen to be aimed, by pure geometric chance, in a path that will eventually pass close by our own sun on their long journey toward us. As those particular rays graze the sun, the curvature of space around that enormous mass bends their path very slightly, exactly the way Eddington observed with starlight during that 1919 eclipse. And because the sun is a sphere, rays approaching from opposite sides of it are bent by precisely the same amount, curving inward and eventually crossing paths again on the far side, converging back toward a single line stretching out into deep space. That line is called the focal line, and it does not begin close to the sun. Because the deflection angle involved is so small, the rays have to travel an enormous distance before they finally converge. The math works out to a starting point of roughly 550 astronomical units from the sun, where a single astronomical unit is simply the average distance between the Earth and the sun. 550 times that distance. And unlike a normal lens, where light converges to a single focal point and then diverges again, this gravitational focal line does not end. It stretches outward toward infinity, meaning that once you have reached that minimum distance, you can continue traveling further out along the line indefinitely, and the focusing effect never switches off. If you were to somehow place a telescope at that distance, 550 astronomical units out, and turn it back toward the sun, you would not see a simple bright star. You would see a sphere of light, the sun itself, surrounded by a faint glowing ring, an Einstein ring, formed from the bent and focused light of whatever object happens to be sitting on the precisely opposite side of the sun from your position. And hidden inside that ring, smeared and distorted almost beyond recognition, would be the light of that distant world. The amplification this effect provides is almost impossible to overstate. In the wavelengths of light visible to the human eye, the sun's gravitational lens boosts brightness by a factor of roughly 100 billion. Sit with that number for a moment, next to the numbers from a few minutes ago. We needed to overcome a contrast problem of 10 billion to 1 between a planet and its host star, and our best coronagraphs could only manage a suppression factor of about 1 million, leaving us 10,000 times short. A gravitational amplification of 100 billion does not just close that gap, it obliterates it with room to spare. It is the equivalent, in raw light gathering power, of building that impossible 90-kilometer mirror we talked about earlier, except instead of manufacturing it out of glass and steel across 14 orders of magnitude of engineering difficulty, nature has already built it for us, quietly out of curved space itself, sitting there the entire time, waiting for anyone patient enough and clever enough to go and use it. And there is a second, quieter gift buried inside this idea, one that solves the contrast problem in an entirely different way than simply overwhelming it with brute amplification. When you use the sun as a gravitational lens aimed at a distant exoplanet, you are never actually looking at the exoplanet's host star at all. You are looking directly at the planet's own light, focused and magnified by our sun. The blinding stadium floodlight from our earlier analogy simply is not in the frame. You still have to block out the light of our own sun, sitting uncomfortably close in your field of view, but that is a problem our existing coronagraph technology is already more than capable of solving. The impossible problem, the 10 billion to 1 contrast ratio that had stalled direct imaging for decades, simply does not exist in this configuration. It has been engineered out of the equation before you even begin. So the plan, in its barest outline, sounds almost absurdly simple once you say it plainly. Choose a planet you want to photograph. Calculate the point on the exact opposite side of the sun from that planet. Send a telescope out along that line, past the orbit of every planet in our own solar system, past the edge of everything humanity has ever physically touched, and once you arrive, turn around, look back at the sun, and photograph the ring of light hiding around it. Which sounds, for a moment, almost easy, until you remember exactly how far 550 astronomical units actually is. and exactly how little of that distance our species has ever managed to cross. Part 3. Farther than anything we have ever built. Voyager 1 launched from Earth in 1977, riding a trajectory that would eventually carry it past every planet in our solar system and out into interstellar space, becoming, in the process, the most distant human-made object in existence. It has been travelling, without pause, for nearly 50 years. It has crossed the orbit of Jupiter, the orbit of Saturn, the orbit of Neptune, and kept going, out past the edge of what most of us casually think of as our solar system, into the strange transitional region where the sun's influence finally begins to fade into the broader galaxy. As of the most recent tracking data, Voyager 1 sits at roughly 169 astronomical units from the sun. It is, by any human measure, extraordinarily far away, and it is not even a third of the way to where we need to go. 550 astronomical units, the minimum distance required to even begin using the sun as a gravitational lens, is more than 3 times farther than the most distant object our species has ever sent anywhere. Sit with that gap for a moment. Voyager 1 represents nearly 5 decades of continuous travel launched during the Cold War, still faintly transmitting data back to Earth with a radio signal so weak it takes over 21 hours just to arrive. And the mission we are describing tonight needs to travel more than 3 times that distance, and then, once it gets there, actually function as a precision scientific instrument for years afterward. The obvious question is simply how fast can we go? And the honest, slightly deflating answer is that conventional rocketry, the kind of chemical propulsion that has powered every crewed launch. Every planetary probe, every mission humanity has ever flown, tops out at speeds around 5 astronomical units per year for a spacecraft on an efficient outbound trajectory. At that rate, a mission to 550 astronomical units would take approximately 110 years to arrive, not to complete its science, simply to arrive. A child born the year such a mission launched would be long dead before it ever reached the point where it could take its first photograph. That timeline is not just impractical, it is, in a very real sense, scientifically meaningless. Science is a human endeavour, carried out by people who want, eventually, to see the results of the questions they spend their careers asking. A mission with 110-year travel time is not a mission anyone alive today will ever see completed. It becomes an inheritance passed down through generations of scientists who will grow old and retire and pass away, still waiting. The engineers working on this problem understood that immediately, and they set themselves a very different, very deliberate constraint. Not can we get there eventually? Can we get there within the working lifetime of a single scientist? Somewhere in the range of 2 to 3 decades from launch to first image. Fast enough that the person who conceived of the mission, or at least their graduate students, might actually live to see what it finds. To hit that kind of timeline, the spacecraft needs to travel at something closer to 25 astronomical units per year, roughly 5 times faster than what chemical rockets can achieve. And there is no chemical fuel, no combustion reaction, no conventional engine in existence capable of delivering that kind of sustained velocity across interplanetary distances. So the engineers working on this mission turned to something stranger, something that does not burn fuel at all, but instead borrows its push directly from the star at the center of our solar system. Light itself, it turns out, carries momentum, even though individual photons carry no mass. This is not a metaphor or an approximation. It is a direct, measurable consequence of Einstein's own physics, the same physics underpinning the gravitational lens itself. When a photon strikes a surface and reflects off it, It transfers a small amount of momentum to that surface, exactly the way a ball bouncing off a wall transfers momentum to the wall, however faint the transferred force may feel. A single photon striking a mirror delivers an amount of push so vanishingly small it would be laughable to try to measure it in isolation. But the sun is not emitting a single photon. It is emitting an almost incomprehensible flood of them, every second, in every direction, and if you build a surface large enough, reflective enough, and light enough. That continuous flood of photons can add up to something genuinely useful. A solar sail. The idea itself is not new. Solar sails have existed as a theoretical propulsion concept for decades, and a handful of small demonstration missions have already tested the basic principle in Earth orbit, proving that sunlight really can push a spacecraft, gently and continuously, without a single drop of propellant burned. But using a solar sail to reach 25 astronomical units per year, fast enough to cross 550 astronomical units within a human lifetime, requires pushing the concept to an extreme nobody has yet attempted. The maneuver the engineering team settled on is, appropriately, called the sundiver. It is exactly as dramatic as it sounds. Rather than launching a spacecraft directly outward and slowly building speed over years using its sail alone, you do something almost counterintuitive. You launch the spacecraft inward first, on a trajectory that carries it plunging deep into the inner solar system, diving toward the sun itself, sail furled and inactive, using the sun's own gravity to whip the spacecraft around like a slingshot and hurl it back outward at tremendous speed. The spacecraft at the center of this plan is designed to weigh less than 100 kilograms fully assembled, a startlingly small mass for something meant to travel farther than any object in human history. As it approaches the sun, still tucked away, still protected, it prepares for the moment that defines the entire mission. At its closest approach, it will pass within roughly 15 million kilometers of the sun's surface, roughly a tenth of the distance separating the Earth from the sun, that is deep inside the orbit of Mercury, into a region of space bathed in radiation and heat far beyond anything a conventional spacecraft could survive parked and stationary. It is precisely at that closest approach that the solar sail deploys. 16 individual rectangular sail segments mounted along a central support truss extending out from either side of the spacecraft's body, unfurling in a matter of moments into a structure with roughly 1,000 square meters of surface area per segment, adding up to something in the neighborhood of 2.5 football fields worth of reflective material, suddenly exposed to sunlight at its most intense and concentrated point anywhere in the solar system. Each individual sail segment can tilt independently, allowing the spacecraft to be steered with precision even as it accelerates, adjusting its angle relative to the sunlight washing over it to fine-tune both its trajectory and the rate at which it gains speed. The material itself has to solve two contradictory problems simultaneously. It has to be almost impossibly thin and light, because every additional gram of mass reduces how effectively sunlight can accelerate the spacecraft, and yet it has to survive conditions that would instantly destroy almost anything else humans have ever manufactured. The proposed sail material is roughly 70 times thinner than a single strand of human hair. A carbon nanotube film coated in a reflective layer of tin, engineered to survive sustained temperatures of around 3,200 degrees Celsius, more than double the melting point of steel. At that temperature, most spacecraft materials would not simply degrade, they would vaporize, as the spacecraft executes its closest pass. The sails are angled precisely perpendicular to the incoming sunlight, capturing the maximum possible push at the exact moment the sunlight is at its most intense, close enough to the sun that the star's gravity is simultaneously providing an enormous velocity boost of its own, a natural slingshot effect layered directly on top of the acceleration from the sail itself. The combination of these two effects, gravitational slingshot and radiation pressure acting together at the point of maximum intensity, is what allows the spacecraft to reach the kind of speed that would otherwise be completely out of reach. The numbers that come out of this maneuver are genuinely staggering. The Sundiver approach is projected to accelerate the spacecraft to roughly 125 kilometers per second, translating to approximately 26 astronomical units of travel per year. At that velocity, the 550 astronomical unit journey that would take a chemically propelled spacecraft over a century collapses down to somewhere in the neighborhood of 20 years. Fast enough, deliberately, precisely fast enough to fall within the working career of the scientists who conceived the mission in the first place. The sails themselves do not last the entire journey. Roughly 2 years after the Sundiver maneuver, once the spacecraft has traveled far enough that sunlight has grown too weak to provide any further meaningful acceleration, the sails are jettisoned entirely, released back into the emptiness of space, their job finished. The spacecraft continues onward under the velocity it has already accumulated, coasting silently through the solar system's outer reaches. Roughly 7 years into the journey, it crosses the current position of Voyager 1, quietly overtaking, in a matter of years, a distance that took humanity's previous most ambitious mission nearly 5 decades to achieve. And then, if everything holds, if every system survives the journey, if the trajectory calculated years earlier remains true across 2 full decades of silent travel through the dark, the spacecraft arrives, 550 astronomical units from home. Positioned, at last, along the focal line of a world we have never seen with our own eyes. But a single spacecraft, alone, that far from Earth, that many years into an irreversible one-way journey, carries an obvious and uncomfortable risk. What happens if something breaks? Part 4. Never sending just one. Imagine the scenario for a moment, because it is worth sitting with honestly before moving forward. 20 years of travel, 20 years of silent coasting through the emptiness between the stars, no repair crew, no backup facility, no way to reach out and physically touch the hardware if something goes wrong. And then, finally, after 2 decades of patient waiting, the spacecraft reaches its destination, 550 astronomical units from home, and something as small as a single failed component, a stuck mechanism, a fried circuit, renders the entire mission useless. 2 decades of travel, years of engineering, and possibly billions of dollars. Reduced to a piece of dead metal drifting silently along a focal line it can no longer use. The engineers behind this mission understood that risk from the very beginning, and their answer to it reshaped the entire architecture of the plan. Rather than building a single, enormous, monolithic spacecraft and betting everything on its survival across a 20-year journey, the mission is designed instead as a swarm. Not one telescope sent out into the dark, but potentially hundreds, launched in coordinated waves, each one small, each one individually replaceable, and each one carrying only a fraction of the total capability needed, so that no single failure can ever end the mission entirely. The basic building block of this swarm is remarkably modest. Each individual launch carries a cluster of 6 small satellites, commonly known as CubeSats, a category of miniaturized spacecraft that has become increasingly capable over the past 2 decades of engineering advances. Within each cluster of 6, every satellite is assigned a specific narrow role. Some carry segments of mirror, the actual light gathering optics that will eventually capture images of the Einstein ring. One is dedicated entirely to a coronagraph, the device responsible for physically suppressing the blinding light of our own sun so the faint ring of planetary light hidden around it can be seen clearly. Another handles communications, relaying data back across the unimaginable distance separating the swarm from Earth. And still another carries a nuclear power source, because at 550 astronomical units from the Sun, sunlight has grown so weak and diffuse that conventional solar panels, the kind that power almost every spacecraft humanity has ever launched into the inner solar system, simply stop being a viable option. Each of these small satellites carries its own miniature solar sail, propelling itself along the same kind of sundiver trajectory as the larger conceptual mission, accelerating outward under its own power rather than relying on a single central spacecraft to carry the entire burden of propulsion. Once launched and accelerated, the cluster of 6 does not remain 6 separate, disconnected pieces of hardware drifting independently through space. They are designed to find one another autonomously using their own onboard sensors and communication systems, and physically assemble themselves into a single, coordinated, mission-ready observatory once they arrive at their destination, without a single human hand ever touching them again after the moment of launch. And here is the detail that quietly reframes the entire scale of the mission. Because the Sun itself is doing almost all of the heavy lifting, gathering and focusing light through its own gravitational field rather than requiring a physically enormous mirror of our own construction. The actual telescope carried by each of these small satellite clusters does not need to be anywhere near the size of the 90-kilometer mirror we would otherwise require. It needs to be, remarkably, only about a meter across. A telescope you could nearly carry in your arms if it were sitting on a table in front of you rather than drifting through interstellar space. The Sun is supplying the light-gathering power. The spacecraft's own optics simply need to be precise enough to capture what the Sun's gravity has already focused and magnified. Even so, a single 1-meter telescope working alone is not enough to reconstruct a usable image from the distorted ring of light surrounding the Sun. The engineering team's models suggest that somewhere between 5 and 6 of these coordinated telescopes, working together, moving in careful, deliberate patterns, are required to extract a clean, reliable image of the Einstein ring. Because the process of pulling a recognizable planetary image out of that warped, circular smear of light is, as we will see shortly, an extraordinarily delicate act of reconstruction, one that benefits enormously from multiple simultaneous measurements taken from slightly different positions. And this is where the ambition of the mission architecture reaches its most striking scale. The plan is not to launch one cluster of satellites, wait patiently for 2 decades, and hope everything survives the journey intact. The plan is to launch an entirely new cluster of 6 satellites every single year, indefinitely, each one accelerating outward along its own sundiver trajectory, each one arriving at a slightly different point along the vast stretch of space leading out to the focal line. Because a full year separates each successive launch, and because each cluster is traveling at roughly the same accelerated velocity, the clusters naturally space themselves apart from one another as they travel, ending up separated by something in the neighborhood of 25 astronomical units, roughly the same distance separating our Sun from the orbit of Neptune. The engineers working on this mission have given this structure an evocative, almost poetic name. They call it the String of Pearls. Picture it precisely as that phrase suggests. A long, gently curving chain of small glittering clusters stretched out from the inner edge of interstellar space all the way out toward the distant focal line, each pearl a small constellation of coordinated satellites, each one launched a year apart from its neighbors, forming together. Something closer to an interstellar highway than a single isolated mission. The advantages of this architecture reach well beyond simple redundancy, though redundancy alone would justify the design. If a single pearl suffers a catastrophic failure somewhere along its 2-decade journey, the mission as a whole does not end. The remaining pearls continue on, unaffected, still carrying their own independent capability to reach the focal line and begin capturing images. But there is a second advantage layered on top of the first, one that speaks to something deeply practical about how long-duration science actually works in the real world. Each successive pearl launched a full year after the one before it, benefits from an entire additional year of advancement in materials science, in computing power, in artificial intelligence, in every incremental improvement that continues accumulating on Earth while the earlier pearls are already deep in transit. A pearl launched in year 5 of the program is not simply a duplicate of the pearl launched in year 1. It is a meaningfully better instrument, built with a year's worth of accumulated engineering progress the earlier pearl never had access to. The pearls also solve a communications problem that would otherwise be almost insurmountable on its own. At 550 astronomical units and beyond, sending data directly back to Earth using conventional radio transmission would involve almost unbearable delays and signal degradation, stretched thin across a distance so vast that light itself takes days simply to make the one-way crossing. Instead, the string of pearls is designed to relay information along its own chain, using laser-based communication links to pass data from the most distant pearl backward, pearl to pearl, gradually working its way inward until it finally reaches a point close enough to Earth for a strong, reliable transmission home. The full image reconstructed from an observation session is projected to total only around 6 megabytes of data, a genuinely tiny amount by modern standards, and yet transmitting that modest file across the entire chain, from the farthest pearl all the way back to mission control on Earth, is expected to take somewhere in the neighborhood of 13 hours, largely a function of the sheer physical distance the signal has to travel, quite apart from any limitation in the technology itself. Taken together, this is not, in any meaningful sense, a single mission in the way we usually think of space missions, with one spacecraft, one launch, and one clearly defined endpoint. It is closer to an infrastructure project, an ongoing, permanent, self-renewing observatory stretched out along the edge of interstellar space, continuously reinforced with fresh hardware every single year, indefinitely, for as long as humanity chooses to keep building pearls and threading them onto the string. And every one of those pearls, every single cluster of satellites launched along this chain, is not actually limited to observing just one planet. Because as it turns out, the Sun does not have only a single focal line pointed at a single fixed target in the sky. It has, quite literally, an infinite number of them. Part 5. An infinite number of doorways. Here is the detail that quietly reframes everything you have just heard, and it is worth sitting with slowly, because it is the point where this mission stops being a single ambitious project and starts becoming something closer to a permanent piece of scientific infrastructure. The focal line we have been describing, the long, narrow corridor of space beginning at 550 astronomical units where the sun's gravity focuses and magnifies light from a distant world, is not a single fixed beam pointed at one predetermined target. Every planet, every star system, Every point of light anywhere in the sky has its own unique focal line, extending outward from the sun in the exact opposite direction from wherever that object sits in space. Think of the sun as the center of an enormous invisible sphere, and imagine drawing a straight line from any distant object through the sun and out the other side. Wherever that line lands, once it crosses the minimum threshold distance, is where that particular object's own focal line begins. Aim at a different planet orbiting a completely different star in a completely different direction, and you get an entirely different focal line, pointed at an entirely different patch of empty space hundreds of astronomical units from Earth. There is no limit to how many of these lines exist. Every single point of light in the night sky has one, waiting patiently for someone to travel out along it. This is what transforms the mission from a single extraordinary photograph into something closer to a permanent capability. Once the underlying technology exists, once the sun diver propulsion works, once the swarm architecture proves itself, once the reconstruction technique for pulling a coherent image out of a distorted Einstein ring has been validated, the mission does not have to stop after a single success. It simply has to choose its next target, calculate a new trajectory, and launch another string of pearls out along a different line. So which targets come first? The engineering team behind this mission maintains a working shortlist built from the very same catalogue of 6,000 confirmed exoplanets that decades of indirect detection have painstakingly assembled. Some candidates are included because they sit comfortably within what astronomers call the habitable zone, the narrow band of distance from a star where temperatures could allow liquid water to persist on a rocky surface. Others are included because of unusual, tantalizing characteristics uncovered through the wobble method or the transit method. Worlds that seem to be tidally locked with one side perpetually facing their star and one side perpetually turned away into darkness, creating a permanent ring of twilight along the boundary between the two, sometimes nicknamed eyeball planets, for the way such a configuration might appear from directly overhead. A bright pupil of habitable twilight surrounded by extremes of frozen night and scorched day. But among the full list of candidates, 3 targets consistently rise to the very top of the priority list, each for its own distinct reason. The third priority is a world orbiting a quiet, stable red dwarf star, roughly a dozen light-years from Earth. Red dwarf stars burn cooler and dimmer than our own sun, and they are, by a wide margin, the most common type of star in the entire galaxy, making up something in the neighborhood of 70% of all stars that exist. This particular candidate receives only a modest amount more radiation from its star than Earth receives from ours, placing it comfortably within a range that many astronomers consider genuinely promising for the possibility of a stable, temperate surface. It has become, in the years since its discovery, one of the most consistently cited candidates for habitability among the entire catalogue of known exoplanets. The second priority is not a single planet at all, but an entire system, one that captured global attention when it was first announced and has remained a centerpiece of exoplanet research ever since. Located a little over 40 light-years from Earth, this system contains not one but 3 rocky worlds sitting either inside or very close to the boundary of their star's habitable zone, all orbiting a single small, dim, red dwarf star tucked closely together in a configuration unlike anything found in our own solar system. What makes this system so valuable for the mission is not just the individual worlds themselves, but the sheer efficiency of the opportunity it represents. Because all 3 planets orbit the same star, a single focal line, and a single string of pearls positioned along it could potentially image multiple separate worlds from one coordinated deployment, multiplying the scientific return of the entire mission without multiplying the number of launches required to achieve it. And the first priority, the single most valuable target on the entire list, is the nearest star system to our own. A small, dim red dwarf sitting just over 4 light-years away, closer to Earth than any other star in the sky, orbited by a planet that sits, by the calculations of the astronomers who discovered it, tantalizingly within the habitable zone. Because it is so close, dramatically closer than any of the other candidates under consideration, it offers something none of the others can match: the highest possible surface resolution achievable anywhere on the target list. If there is meaningful detail to be found on any exoplanet's surface using this technique, continents, ice caps, weather systems, or something far stranger and more consequential, this is the world where the mission's engineers believe we stand the best chance of actually resolving it clearly enough to know for certain. Picture, for a moment, what the completed architecture actually looks like once all of this comes together. Not a single spacecraft racing toward a single fixed destination, but a growing web of focal lines radiating outward from our own solar system in every direction, each one aimed at a different candidate world, each one slowly, patiently populated with its own string of pearls. Launched a cluster at a time, year after year, decade after decade. Some lines carrying a single dedicated observatory aimed at one especially promising planet. Others, like the line aimed at that nearby 3-planet system, potentially serving double or triple duty, imaging multiple worlds from a single coordinated deployment. It is worth pausing here to notice something almost philosophical about the shape of this plan, because it says something quietly profound about how this particular problem in astronomy differs from almost every other frontier science has pursued. Most great scientific instruments are built once, pointed carefully, and used for a fixed span of years before being decommissioned and replaced by whatever comes next. The Hubble Space Telescope, the James Webb Space Telescope, each one an enormous singular investment, a singular capability, eventually retired and succeeded. But this is not that kind of instrument. This is closer to an ever-expanding network, a permanent capability that once established never stops growing, never stops adding new lines, new pearls, new candidate worlds, waiting patiently to be photographed for the very first time. And each new pearl added to each new focal line is not just an incremental addition to a static catalogue. It represents, potentially, an entirely new world handed to humanity, a planet that has existed for billions of years, orbiting quietly, unseen, finally rendered visible because a small cluster of satellites, no larger than a few meters across in total, managed to travel 550 astronomical units from home and look back at the right angle at the right moment, along a line of light that had been waiting there the entire time, doing nothing, simply because nobody had yet arrived to look through it. But knowing where to point the telescope, and even successfully arriving there after 2 decades of travel, is still only half of the problem. Because when that swarm of satellites finally does arrive, finally does turn its optics back toward the sun, what greets them is not a clean, simple photograph waiting to be captured. It is something far stranger. A warped, distorted ring of light wrapped entirely around the blazing disk of our own star, with the image of an entire alien world smeared and folded somewhere inside it, hidden in plain sight, waiting to be pulled back out through nothing but mathematics. Part 6. Unraveling the Ring. Here is where the mission stops being primarily an engineering problem and becomes something closer to pure mathematical detective work. And it is worth slowing down here, because this is genuinely one of the more elegant pieces of physics involved in the entire plan. Imagine for a moment that the swarm has already arrived, 20 years of travel behind it, 550 astronomical units from home, sails long since jettisoned, telescopes finally powered on and oriented back toward the distant, shrinking disk of our own sun. What appears in that view is not a simple photograph of a planet, it is something considerably stranger. A bright, glowing sphere of sunlight, surrounded not by a clean, single point of planetary light, but by a thin, curving, luminous ring wrapped entirely around the sun's circumference. Somewhere within that ring, distorted almost beyond recognition, is every photon of light that ever left the surface of the target planet and happened, by pure geometric chance, to pass close enough to our sun on its long journey outward to be bent back toward this exact point in space. The reason the image arrives as a ring rather than a simple dot has everything to do with the shape of the sun itself. Because the sun is roughly spherical, light from the distant planet can approach it from literally any angle around its circumference and still be bent inward toward the same eventual focal line. Light grazing the top of the sun bends downward. Light grazing the bottom bends upward. Light grazing the left edge bends rightward, and light grazing the right edge bends leftward. Every one of these paths, approaching from every possible angle around the sun's circumference, converges back toward roughly the same distant point in space. And because the geometry treats every direction around the sun equally, the resulting image is not a single beam or a single point of focused light. It is smeared symmetrically into a complete circle, a ring wrapped entirely around the sun's glowing disk. Here is the crucial, almost counterintuitive detail buried inside that ring. The full image of the planet, every point on its surface, every continent and ocean and polar ice cap, if such things exist there at all, is not compressed down into that single narrow ring the way you might intuitively expect. Instead, general relativity predicts that the complete image of the planet gets projected outward from the focal line into a much larger three-dimensional shape, something closer to a long, wide cylinder stretching out along the direction of travel, rather than a flat circle sitting at a single fixed point. For the nearest, most promising candidate world on the priority list, the mathematics work out to an imaging cylinder roughly 32 kilometers wide once the observing telescopes reach the minimum required distance of 550 astronomical units. And as the swarm continues traveling further outward along the focal line, deeper into interstellar space, that cylinder does not shrink. It grows, expanding in a roughly linear relationship with distance, so that by the time the telescopes have travelled out to somewhere in the range of 1200 astronomical units, the imaging cylinder has widened to something closer to 57 kilometers across. The practical implication of this is almost startling once you fully absorb it. The mission does not need to hold perfectly still at a single fixed point and simply snap one photograph. It needs to physically move its telescopes through this expanding cylindrical volume of space, methodically, deliberately, sampling the light arriving at many different positions within it, because the image of the planet is not sitting still at one location. It is smeared and distributed continuously throughout this entire three-dimensional region, and the only way to reconstruct it is to sample it, piece by piece, point by point. This is where the coordinated cluster of telescopes within each pearl earns its purpose. The mission plan calls for the imaging cylinder to be conceptually divided into a fine grid, and each individual square within that grid corresponds ultimately to a single pixel in the final reconstructed image of the planet's surface. For the nearest priority target, Imaged at the minimum focal distance, each of those grid squares works out to a physical separation of roughly 31 meters. That is the level of positional precision the telescopes have to achieve. Out at 550 astronomical units from Earth, with no possibility of course correction from ground control in anything resembling real time, given that even a radio signal travelling at the speed of light takes days simply to make the one-way trip. But there is a second, equally stubborn problem sitting on top of this positional challenge, and it comes directly from the Sun itself. The Sun is not a calm, quiet, uniform sphere of light. It has an active, turbulent corona, a shifting halo of superheated plasma extending outward from its visible surface, constantly flickering and fluctuating in brightness. Any attempt to isolate the faint ring of planetary light wrapped around the Sun's disk has to somehow account for and subtract away this constantly shifting background noise. Or the delicate signal from the distant planet, already amplified by gravity but still working against the sheer overwhelming brightness of a nearby star, will simply be lost inside the noise of the corona's own flickering. The engineering solution to this problem is elegant precisely because it is so simple in concept. Within each pearl of the several 1-meter telescopes working in coordination, one is deliberately positioned outside the imaging cylinder entirely, aimed at the Sun but sitting just beyond the region where any of the planet's light would ever fall. That telescope captures, essentially, a pure, uncontaminated measurement of the Sun's corona at that exact moment, with none of the faint planetary signal mixed in. Meanwhile, the remaining telescopes, positioned within the imaging cylinder itself, capture the full combined picture, Sun, corona, and the faint hidden ring of planetary light all layered together. By digitally subtracting the clean corona measurement from the combined measurement, the mission is left with something remarkably close to a pure signal, the corona's noisy contribution mathematically stripped away, leaving behind primarily the faint, precious light that actually originated from the distant world. Each individual telescope, moving carefully into its designated position within the grid, spends somewhere between 30 and 60 seconds capturing its portion of the ring before repositioning and moving on to the next grid square. Multiply this process across the entire grid, across every pearl positioned along the focal line, across months and years of patient, methodical observation, and the mission slowly accumulates an enormous archive of individual measurements. Each one a tiny fragment of the full picture, none of them meaningful in isolation, but together forming the raw material for something extraordinary. There is a further complication worth mentioning, because it speaks to just how demanding this reconstruction process really is. The Sun, it turns out, is not a perfect sphere. Like most rotating bodies, it bulges very slightly at its equator and flattens very slightly at its poles, a subtle geometric imperfection known as oblateness. As the observing telescopes move further out along the focal line, this small asymmetry begins to distort the shape of the Einstein ring itself, causing it to brighten unevenly, growing brighter along one arc while dimming along another, eventually splitting at sufficient distance into two distinct bright arcs rather than remaining a single continuous circle. The engineering team has to account for this shifting geometry continuously, recalculating and adjusting their imaging strategy as the swarm travels further from the Sun and the shape of the ring itself continues to evolve. So after months, potentially years, of this painstaking process, what the mission finally accumulates is not a photograph in any conventional sense. It is an enormous archive of individual measurements, grid coordinates paired with corona subtracted light readings, spread across an expanding cylindrical volume of space, hundreds of thousands or millions of individual data points, none of which, on its own, resembles anything like a planet. This is where general relativity offers one final crucial gift. The exact mathematics describing how the sun's gravity bends and distorts light, the same equations Einstein worked out over a century ago, can be used to precisely calculate something called a point spread function. Essentially a detailed mathematical map describing exactly how any single point of light on the planet's surface gets smeared, bent and redistributed across the Einstein ring by the time it reaches the observing telescopes. And crucially, this process works in reverse. If you know precisely how a point of light gets distorted on its way to you, you can run that same mathematical process backward, taking the actual distorted light you measured and reconstructing, point by point, where on the planet's surface it must have originated from. It is, in a very real sense, an act of controlled, deliberate undistorting. Millions of individual, meaningless-looking measurements, each one representing a tiny fragment of light gathered from one small position within the imaging cylinder, run backward through the known mathematics of gravitational lensing, gradually assembling themselves pixel by pixel into something that begins, slowly and unmistakably, to resemble a picture. Not of the sun, not of empty space, of an entire other world 4 light-years away, rendered visible for the very first time in the entire history of our species, not by travelling there, not by sending a probe to fly past it, but by patiently, mathematically, unwinding the light that world had been quietly sending out into the universe the entire time. Part 7. What the picture might show. Sit with the sheer strangeness of the process for a moment before we move forward, because it is easy, hearing it laid out this cleanly, to lose track of how genuinely radical the underlying idea actually is. Nothing about this method involves travelling to another star. No spacecraft crosses the 4 light-years separating us from that nearest priority world. No probe ever passes within visual range of its surface. Every fragment of information in the final image originates from light that world was already emitting or reflecting into space, regardless of whether anyone was watching. Light that happened to pass near our own sun purely by geometric chance, bent inward by gravity, gathered patiently over months or years by a small fleet of modest telescopes, and reconstructed afterward using nothing but mathematics that Einstein worked out over a century ago, while doubting anyone would ever find a practical use for it. And the resolution this method is projected to deliver is not modest. For the nearest priority target, sitting just over 4 light-years from Earth, the engineering models suggest each individual pixel in the final reconstructed image would correspond to roughly 1 kilometre of surface detail on the planet itself. Sit with that number because it deserves to be sat with. 1 kilometre per pixel on a world 4 light-years away, using a network of telescopes each no larger than a metre across. For comparison, weather satellites orbiting Earth today, hovering just a few hundred kilometres above the surface, routinely produce imagery at resolutions considerably coarser than that. This mission, reaching across a distance so vast that light itself takes over 4 years to cross it, is designed to outperform some of our own planet's weather satellites in raw surface resolution. At that level of detail, the mission's own projections describe an image that would not merely confirm the presence of a rocky world. It would begin to reveal its actual geography. Continental outlines, distinguishable from open ocean by contrast and colour. Mountain ranges, visible as distinct textured regions where elevation changes catch and scatter light differently than the surrounding lowlands. Polar ice caps, if they exist, standing out starkly bright against darker terrain nearby, exactly as Earth's own poles appear brilliant white in photographs taken from space. Deserts and forests and grasslands, each with their own distinct color signature, different enough from one another to be distinguished even at kilometer-scale resolution. Weather systems, potentially, including something as specific and identifiable as a hurricane, a swirling spiral pattern of cloud cover that would be difficult to mistake for anything else. Evidence not just of a planet with an atmosphere, but of an atmosphere actively, dynamically in motion. And then there is the possibility that sits quietly underneath everything else in this entire project, rarely spoken aloud in the early engineering papers, but unmistakably present in the ambition of the whole endeavour. At kilometre-scale resolution, sustained and refined over months of repeated observation as the swarm continues gathering data and the reconstruction techniques continue improving, it may become possible to distinguish structures that do not occur naturally. Geometric patterns. Straight lines cutting across otherwise organic, irregular terrain. Clusters of light, if the observation happens to catch the planet's night side, concentrated in patterns inconsistent with anything geological or meteorological. Cities, in other words, or whatever an alien civilization's version of a city might look like from a kilometre away, rendered not as science fiction speculation, but as an actual, testable outcome of a real astronomical technique grounded in general relativity. It would be irresponsible to overstate this possibility, and the scientists actually working on this mission are careful never to promise anything of the sort as a guaranteed outcome. There is no evidence yet, from any indirect detection method, that any of the mission's priority targets host any form of life at all, intelligent or otherwise. But the entire point of building an instrument this powerful, precisely engineered to resolve kilometre-scale detail on a world 4 light-years away is that it removes the need to guess any longer. Whatever is actually there, continents or oceans or ice or forests or, however unlikely, something built, would become visible rather than inferred. For the first time in the history of our species, the question of what another world actually looks like would stop being a matter of speculation and simply become a matter of looking. And the mission's ambition does not stop at simple visual imagery, however extraordinary that alone would be, because the same light being gathered and reconstructed carries far more information embedded within it than just colour and shape. Light interacting with a planet's atmosphere, passing through gases before reflecting off the surface or scattering back out into space, carries the specific spectral fingerprints of whatever molecules the atmosphere contains. Distinct wavelengths absorbed or emitted in patterns unique to each chemical compound, the same basic principle astronomers have already used with far cruder instruments to make educated guesses about the atmospheric composition of transiting exoplanets from indirect starlight measurements alone. With an instrument capable of gathering not just aggregate atmospheric light from the entire planet at once, but spatially resolved light tied to specific locations on the planet's actual surface, the mission's data could, in principle, do something no previous exoplanet observation method has ever come close to achieving. It could map where on the planet particular atmospheric gases are concentrated. If a substantial signature of methane, a gas that on Earth is overwhelmingly produced by biological activity, appeared strongly over one specific continent or forested region and weakly elsewhere, that would not just be evidence of an interesting atmosphere in the abstract. It would be a location, a place on another world where something, geological or biological, is actively producing a gas closely associated, at least on our own planet, with the presence of life. Layer years of repeated observation on top of that, and the possibilities extend further still. Watching the same planet, the same continents, the same weather patterns across months and then years of accumulated imaging would allow researchers to track genuine change over time. Seasonal shifts in ice cover, expanding and retreating with the planet's own orbital rhythm. Weather systems forming, travelling, and dissipating in patterns that could be studied and modelled the same way meteorologists study storm systems here on Earth. Evidence of active geology. If the world in question has plate tectonics or volcanic activity, might reveal itself gradually through subtle shifts in surface features or atmospheric composition, observed and catalogued not from a single photograph, but from a genuine, ongoing, long-term study of an entire living, changing planet 4 light years from the one you are lying on right now. And it is worth remembering, once more, that this entire capability is not limited to a single world. Every additional pearl launched along a new focal line adds another entire planet, or in the case of that especially efficient 3-world system further down the priority list, potentially adds several planets at once to a growing catalogue of worlds under continuous, detailed, long-term observation. The mission, once fully realized, would not produce a single historic photograph and then conclude. It would establish something closer to a permanent, expanding planetary surveillance network, quietly built along the edge of interstellar space, patiently watching a growing collection of distant worlds, indefinitely, for as long as humanity continues choosing to add new pearls to the string. It is an extraordinary thing to consider, lying there in the dark tonight, that the barrier standing between humanity and an actual photograph of another living world, complete with continents and weather and perhaps something more, was never really a lack of imagination. Scientists have wondered about this exact question, in one form or another, for as long as there have been scientists, and long before that too, for as long as there have been people willing to lie back and stare upward into the dark and wonder what might be looking back. What was missing this entire time was simply a way to bend enough light. And it turns out the universe had already built exactly the tool required for that job, sitting quietly at the center of our own solar system this entire time, waiting patiently, doing nothing in particular, until someone finally worked out how to use it. Part 8. Where the plan actually stands. It is worth pausing here, gently, and asking the question every good sleep documentary eventually has to confront honestly. Is any of this actually happening, or is it simply an elegant thought experiment, dressed up convincingly in real physics, but destined to remain forever theoretical? The kind of idea that gets discussed in academic papers and quietly shelved. The honest answer, and it is a genuinely reassuring one, is that this is not simply a thought experiment. It is a real, funded, actively developed research program, moving through a formal evaluation process at NASA specifically designed to identify and nurture exactly this kind of ambitious, high-risk, high-reward idea. The program responsible is called the NASA Innovative Advanced Concepts Program, often shortened simply to NIAC, and its entire purpose is to fund early-stage research into ideas that sound, on first hearing, almost too ambitious to be real, but that are nonetheless grounded in legitimate, testable physics. It exists precisely for proposals like this one, ideas that fall well outside the conservative incremental improvements that make up the bulk of ordinary space mission planning, and that require patient, staged development before anyone can responsibly commit to building actual flight hardware. The mission moves through this program in distinct phases, each one more demanding than the last, and each one requiring the research team to prove, with increasing rigor, that their idea is not merely appealing in principle, but genuinely achievable in practice. Phase 1 of this particular concept was completed in 2017. The central goal of that first phase was deceptively simple to state and enormously difficult to actually demonstrate. The research team needed to show, through rigorous calculation and simulation, that a modest 1-meter telescope, positioned at the minimum required distance of 550 astronomical units, really could, according to the known laws of physics, successfully image an exoplanet using the Sun's gravitational lens. This was not yet an engineering study. It was a physics study, a fundamental proof that the underlying concept was not just theoretically elegant, but practically sound, that the numbers actually worked out the way decades of scattered academic literature had suggested they might. They passed. The laws of physics, when worked through in careful, exhaustive detail, allowed it. Phase 2 followed in 2018, funded with roughly $500,000, and it moved the project from raw physics into genuine engineering territory. 3 critical breakthroughs emerged from this stage of the work. First, the team worked out in real mathematical detail exactly how to reliably extract a coherent planetary image from the distorted light of an Einstein ring. The very reconstruction process described a few minutes ago, transforming a warped, symmetric ring of light back into recognizable surface geography through inverted point spread function mathematics. Second, they developed the swarm architecture itself, the string of pearls concept, working out how a distributed network of small, coordinated satellites could accomplish what a single, impossibly large spacecraft could not. And third, and perhaps most critically, they demonstrated that solar sail propulsion executed through a sundiver maneuver could realistically deliver a spacecraft to the required distance within a scientifically meaningful time frame, rather than the century-plus journey that conventional propulsion would demand. Phase 3 began in 2020, and it represents the outer edge of what the NASA Innovative Advanced Concepts Program currently supports. In the entire history of the program, only 3 concepts have ever advanced this far, a detail that gives some sense of just how selective and demanding this final stage actually is. The team received roughly $2 million in funding, and their task shifted once again, this time toward building a complete, integrated mission architecture, running detailed simulations across every stage of the plan, from launch through solar sail deployment, through the 2-decade cruise phase, through the actual imaging and reconstruction process itself, in order to answer a single, very direct question for NASA. If you fund this properly, at full scale, will you actually get the image you are promising? Beyond the formal NASA funding pathway, the lead researcher behind this concept has also secured private philanthropic funding from an undisclosed foundation, specifically to build and fly an early demonstration spacecraft, one designed to test the solar sail technology and the sundiver maneuver directly in space, at smaller scale, well before any full mission is ever committed to. That demonstration spacecraft is intended to launch within the next couple of years, a genuine physical test flight of the propulsion concept that the entire rest of the mission ultimately depends on. So what would the complete, full-scale version of this mission actually cost if every phase were funded through to completion? The team's own estimates place the total cost, spread across roughly 4 decades of continuous development, launches and operations, at somewhere in the neighborhood of $40 billion. Broken down across that time frame, that works out to something close to $1 billion a year, sustained, year after year, for the better part of half a century. It is worth placing that number beside a few honest points of comparison, because in isolation, $40 billion sounds, understandably, like an almost unimaginable sum. And yet the International Space Station, a single orbiting laboratory circling a few hundred kilometers above our own planet, has cost roughly 5 times that amount to build and operate across its lifetime. The Apollo program, which carried 12 human beings to the surface of the moon and back across a handful of historic missions in the 1960s and early 1970s, cost, adjusted into modern terms, something in the range of 20 times more than this mission's total projected budget, placed against either of those two landmark achievements in the history of spaceflight. A project aiming to deliver humanity's first genuine photograph of another living world, complete with continents, weather, and potentially direct evidence of extraterrestrial life, does not look quite so extravagant. And there is one further comparison worth sitting with quietly, because it reframes the scale of the question entirely. Global military spending, taken in aggregate across the world's major powers, runs into the billions of dollars every single day. Depending on which nation's budget you examine, a sum equivalent to this mission's entire $40 billion, 4-decade cost could, in principle, be raised and spent within a matter of weeks, if any single government or coalition of governments chose to prioritize it. This is not a statement about what any nation should do with its resources. It is simply a way of understanding that the barrier standing between humanity and this mission has never really been a lack of money in any absolute sense. It has been a lack of sustained collective will. If this mission ever does move forward at full scale, it is difficult to imagine it remaining the work of a single space agency alone. A project spanning 4 decades, requiring continuous funding, continuous engineering refinement, continuous coordination across dozens of individual launches, each one contributing a new pearl to an ever-lengthening string stretching out toward the edge of interstellar space, is the kind of undertaking that tends to eventually draw in international partnership, the way the largest, longest-running scientific instruments on Earth and in orbit so often do. A truly global effort, built collaboratively, aimed at answering a question every human civilization throughout history has, in one form or another, quietly asked while looking up at the night sky. And so here is where the story actually stands, right now, tonight, as you lie there listening. This is not idle speculation. It is not a comforting bedtime fantasy layered over borrowed physics. It is a real program, moving through real, rigorous evaluation, funded, staged, tested, piece by piece, with a demonstration spacecraft already planned to fly within the next couple of years to prove the propulsion technology directly. Whether the full $40 billion, 4-decade version of this mission is ever actually built remains, honestly, an open question, dependent on funding decisions and political will that no engineer, however brilliant, can fully control. But the physics is sound. The individual pieces have each been separately tested and validated, and somewhere, quietly, patiently, a small team of scientists is working toward a very specific, very personal goal, not simply to prove that this idea could work in theory, but to actually see the image with their own eyes within their own working lifetimes before they are too old to appreciate what they have found. Part 9. A conversation between two suns. There is a version of this idea that reaches even further than the mission itself, and it is worth sitting with slowly, because it quietly reframes everything you have heard so far. Imagine, for a moment, that the swarm eventually reaches its destination. Imagine the reconstruction succeeds, and somewhere in that painstakingly assembled image, continents resolve into view and weather systems swirl visibly across an alien atmosphere, and perhaps, faintly, unmistakably, something geometric catches the eye in a pattern nature does not usually produce on its own. What happens next? Not scientifically, emotionally, practically, what does humanity actually do the morning after that image arrives? The instinct, almost immediately, would be to try to say something back. And it turns out the very same physics responsible for the imaging half of this mission also offers a startlingly elegant answer to that instinct, one that von Eschleman himself glimpsed all the way back in 1979, decades before anyone had the technology to seriously attempt it. Every star in the galaxy, not just our own sun, is capable of acting as a gravitational lens, focusing and magnifying light, and by extension, any signal riding along with that light in exactly the same way our sun does. The distance at which this focusing effect begins to work depends on the mass of the star in question. More massive stars bend space more dramatically, which means their focal region begins closer in. Less massive stars bend space more gently, pushing their focal region further out. The type of star that happens to dominate the galaxy's overall population, the small, cool, dim red dwarfs that make up something in the neighborhood of 70% of all stars in existence, tend to have focal regions beginning at roughly half the distance required for our own sun, somewhere in the neighborhood of 250 astronomical units rather than 550. Now, instead of imagining a telescope sitting at that focal point, gathering incoming light from a distant world, imagine something different. Imagine a receiver instead. A device built not to capture faint reflected sunlight bouncing off a planet's surface, but to detect deliberate, intentional signals sent by whoever or whatever might be occupying that focal point on the opposite end of the connection. Here is the thought experiment worth holding on to. Suppose humanity places a receiver at the gravitational focus of our own sun, out along that same 550 astronomical unit focal line already required for the imaging mission. And suppose, somewhere else entirely, an alien civilization orbiting a nearby star has done precisely the same thing, positioning a receiver of their own at the gravitational focus of their star, aimed back toward us. Any signal we choose to transmit toward them gets caught, focused, and dramatically amplified by their star's own gravity before it ever reaches their receiver. And any signal they choose to send back toward us gets caught and amplified in exactly the same way by our own sun's gravity, long before it arrives at whatever instrument we have, waiting at the far end of our own focal line. The amplification involved is not a modest improvement. The gravitational lens effect, applied specifically to this kind of communication link, is calculated to boost signal strength by a factor in the neighborhood of 1 billion, and the practical consequence of that kind of amplification is almost difficult to believe. According to the underlying calculations, an error-free, reliable data connection between our own solar system and the very nearest neighboring star system would require a transmitted signal strength of only about 1/10,000th of a watt. For context, the ordinary transmitter inside a smartphone sitting in someone's pocket right now uses something in the range of 2,000 times more power than that to send a text message across a few kilometers to the nearest cell tower, and this need not even be limited to old-fashioned radio transmission. Using modulated light instead, an optical data link rather than a radio one, allows dramatically more information to be encoded within the same signal, simply because light waves oscillate far more rapidly than radio waves and can therefore carry far more data per second. Run the calculations through, and the projected bandwidth of a fully realized gravitational lens communication link between neighboring star systems works out to something in the range of 10 megabytes per second. Fast enough, in practical terms, to stream high-definition video without interruption across a distance of light years using a transmitter weaker than the one already sitting in your pocket right now. To achieve anything close to that same result without the gravitational lens doing the heavy lifting, you would need something entirely different. A dish 50 kilometers wide, replacing whatever modest receiver you might otherwise use, and a transmitter drawing something close to the entire electrical output of a small city, replacing that fraction of a watt signal. The star itself, sitting there quietly, doing nothing you have to build, doing nothing you have to power, hands you both of those staggering upgrades entirely for free, purely as a consequence of the geometry of curved space. Sit with the implication of that for a moment, because it extends well beyond a single conversation between two neighboring star systems. If this kind of link is genuinely achievable, then in principle, every star system in the galaxy capable of positioning a receiver at its own gravitational focus becomes a potential node in something that starts to resemble an actual network. Not a metaphorical network. In the loose sense, astronomers sometimes use the word when discussing loosely connected radio observations. An actual, physical, functioning communication network spanning potentially the entire galaxy, in which messages could travel from star system to star system, each link amplified nearly for free by the gravity of the stars themselves, carrying real bandwidth at the literal speed of light across distances that would otherwise make any kind of meaningful interstellar conversation completely impractical. There is a name that has occasionally been used, half seriously, half playfully, for this kind of speculative structure, and it is worth saying it aloud, if only because it captures the scale of the ambition so cleanly. A galactic internet. And here is the detail that should genuinely unsettle you, gently, the way the best kind of scientific mystery does, right before sleep. If this idea is sound, if the physics genuinely works the way the calculations suggest it should, then there is no requirement that humanity be the first civilization to think of it. Any sufficiently advanced civilization, anywhere in the galaxy, capable of basic spaceflight and basic gravitational physics, would eventually arrive at the exact same realization von Eschleman arrived at back in 1979, sitting quietly in an academic paper for decades before anyone had the technology to seriously pursue it. And if any of them had already built a receiver, already positioned it precisely at the gravitational focus of their own star, already begun transmitting, quietly, patiently, in whatever direction seemed most promising, that signal could, in principle, already be sitting there, waiting, somewhere along a focal line we have simply never had a reason to visit. We would never have heard it, not because it was not sent, simply because nobody has ever positioned a receiver at the one specific location in space where it would arrive amplified enough to actually detect. It is worth being careful and honest here. The way this entire mission has tried to be careful and honest at every stage. This remains, for now, entirely speculative. No signal has been detected, no receiver has been built. This is not evidence of anything, only a description of what becomes theoretically possible if the same physics enabling the imaging mission is turned, instead, toward listening rather than looking. But it is a genuinely strange thought to carry with you into sleep tonight, that the very same quiet stretch of curved space our own sun has been bending patiently for billions of years, entirely without anyone's involvement, might already be doing exactly this favor for someone else, somewhere else, and the only reason we have not noticed is that nobody has ever gone far enough out along the right line to listen. Part 10. the lens at the center of everything. There is one more thought experiment worth walking through before we begin to close tonight, and it is the kind of idea that tends to arrive quietly, almost as an afterthought, and then refuses to leave once you have actually sat with it. Because if a star the size of our own sun can bend light enough to build a telescope with the effective power of a 90-kilometer mirror, the obvious, almost unavoidable question follows naturally. What happens if you replace the star with something considerably larger? At the very center of our own galaxy, roughly 26,000 light-years from where you are lying right now, sits an object unlike anything else this mission has discussed so far. A supermassive black hole, the gravitational anchor around which every star in the Milky Way, including our own sun, slowly orbits across timescales of hundreds of millions of years. Its mass is estimated at somewhere in the neighborhood of 4 million times the mass of our own sun. Compressed down into a region of space so small and so dense that not even light, moving at the fastest speed anything in the universe is permitted to travel, can escape its gravitational grip once it crosses a certain boundary. Gravitational lensing amplification, it turns out, scales in a fairly direct, straightforward way with the mass of the object doing the lensing. A star 4 million times more massive than our Sun does not simply lens light a little more effectively. It lenses light with an amplification factor roughly 4 million times greater. Numbers at that scale become difficult to hold on to intuitively, but it is worth trying anyway, because the implications reach further than almost anything else discussed tonight. And there is a second advantage layered on top of that staggering increase in raw amplification, one that solves several of the most stubborn engineering headaches involved in the solar version of this mission entirely by accident. Our own Sun, as useful as it is for gravitational lensing, is also, fundamentally, a hot, bright, physically enormous, and constantly turbulent object. It has a surface. It has an active corona, flickering and fluctuating, requiring careful subtraction from every single measurement. It has a physical radius large enough that light cannot simply pass directly through its gravitational center, forcing every calculation to work around its actual bulk, which is precisely why the minimum focal distance for our Sun sits so far out, at 550 astronomical units, rather than closer in where the pure mathematics of gravitational bending alone might otherwise allow. A black hole has none of these problems. It has no physical surface to block incoming light. It has no glaring corona demanding constant background subtraction. Light passing near a black hole, rather than being stopped by a solid physical body the way it would be near our own Sun, can pass extraordinarily close to the gravitational center itself, skimming just outside the boundary known as the photon sphere, a region so close to the black hole that light can, under the right conditions, actually be bent into a complete orbit around it before continuing on its way. Because there is no physical obstruction forcing light to stay a safe distance away, there is no equivalent minimum focal distance requirement standing between an observer and the black hole's full lensing potential. Run the numbers through, and the results stop sounding like careful, sober astronomical projections and start sounding almost uncomfortably like something out of speculative fiction, except every figure involved comes directly from established general relativity, the same physics already validated and confirmed through more than a century of observation. Position a hypothetical telescope roughly 1 light-year from the galaxy's central black hole and aim it toward a planet sitting on the completely opposite side of the galaxy, some 100,000 light-years away. According to the underlying calculations, the resolution achievable at that staggering distance would be sharp enough to make out individual buildings on the planet's surface. Not continents, not cities as vague clusters of light. Individual buildings on a world 100,000 light-years away, using the gravitational lens of our own galaxy's central black hole in exactly the same way the solar mission plans to use our sun. Push the thought experiment further still. Aim that same hypothetical telescope not at a planet somewhere within our own galaxy, but at a planet orbiting a star inside the Andromeda galaxy, our nearest large galactic neighbor, sitting some 2.5 million light-years away. The projected resolution at that almost incomprehensible distance still works out to somewhere in the neighborhood of 1 kilometer per pixel. Read that sentence again slowly, because it deserves to be read slowly. A planet 2.5 million light-years away, imaged more clearly, at finer resolution than the solar mission's own nearest priority target, sitting just over 4 light-years from Earth. And the thought experiment does not even need to stop there. Extend it one final step and aim that same hypothetical instrument toward the Virgo cluster, an enormous, densely packed collection of thousands of galaxies sitting roughly 4 million light-years from our own. According to the same calculations, even at that almost unimaginable distance, you could, in principle, still resolve continents, still resolve oceans, potentially still resolve exactly the kind of geometric, artificial-looking patterns that might indicate something built rather than something grown. Let that fully settle for a moment before we move on, because it is genuinely one of the strangest implications buried anywhere within this entire subject. The universe appears to have constructed, entirely by accident, purely as a consequence of how massive objects warp the space around them, an instrument sitting quietly at the center of our own galaxy capable, in principle, of resolving individual continents on worlds tens of millions of light-years away. A telescope more powerful than anything humanity could ever hope to construct through conventional engineering, sitting there, unused, doing nothing for the entire history of our species, simply because nobody has ever had a way to actually get close enough to make use of it. And that final clause carries the entire weight of why this remains, for now, nothing more than a thought experiment rather than an active NASA proposal. Even travelling at 99.9999% of the speed of light, a velocity so extreme it edges up against the fundamental limits the universe permits for anything with mass. The journey to the galaxy's central black hole would still take somewhere in the neighbourhood of 26,000 years. And that number does not even account for the almost unfathomable engineering challenge of building anything capable of surviving that close to a black hole's environment in the first place, let alone accelerating a spacecraft to a fraction of light speed so extreme it exists at the very edge of what physics currently allows us to seriously contemplate. So for now, this remains exactly what it has been from the moment the thought first occurred to anyone patient enough to run the numbers. A genuinely real, genuinely valid extension of the same physics underlying the solar mission, mathematically sound in every respect, and completely, hopelessly beyond anything humanity could realistically attempt within the coming centuries. It sits there in the background of this entire story, not as a plan, but as a reminder of just how much more the universe is capable of than the corner of it we currently have any hope of reaching. A reminder that somewhere at the heart of our own galaxy, entirely unused, sits an instrument that could, in principle, show us continents on worlds 50 million light-years away. And that the only thing standing between us and using it is 26,000 years of travel time and an engineering problem so far beyond our current capability that it barely qualifies as a proposal at all. But the solar version, the version built around our own quiet, ordinary star, rather than the monster sitting at the galaxy's center, remains genuinely within reach. Not easy, not simple, not guaranteed, but within reach in a way that this final galaxy-spanning thought experiment simply is not, at least not for many generations still to come. Part 11. The question waiting at the edge of the ring. Bring the story back down now, gently, from the scale of galaxies and black holes to the scale of a single research team working through their own careers, funded a couple of $1 million at a time, quietly building toward a specific concrete goal that they genuinely believe they might live to see. Because underneath all of the staggering numbers, the 550 astronomical units, the $40 billion, the 20 years of travel, the 100 billion times amplification, there is something almost startlingly personal sitting at the heart of this entire mission. The researchers involved have been explicit about this from the beginning, in a way that is fairly unusual for a project of this scale. They are not simply designing a mission for some abstract future generation of scientists to eventually inherit and complete. They are deliberately, carefully constraining the entire architecture of the project around a single practical requirement, that the people who conceive of it should be able to live long enough to see the results. That is why the Sun Diver maneuver exists at all. That is the entire reason for choosing solar sails and gravitational slingshots over the far slower, far more conventional chemical propulsion that would otherwise take over a century to reach the same destination. Every major engineering decision in this mission traces back, in some fashion, to that same underlying human motivation. Not simply can this be done, but can this be done in time for the people doing it to witness the outcome? There is something quietly moving in that constraint once you sit with it. Most of the largest scientific undertakings in human history have been built by people who understood, going in, that they would never personally witness the full completion of their work. Cathedral builders in medieval Europe who laid foundation stones for structures that would not be finished until long after their own deaths. Astronomers cataloguing the positions of stars, decade after decade, patiently building data sets intended for researchers not yet born. This mission is deliberately, consciously different. It is built by people who want to see it finished, who are racing, gently but genuinely, against their own mortality, trying to compress a journey that pure physics would otherwise stretch across more than a century into something closer to 20 years. Precisely so that a working scientist, still active in their career, might actually stand in a control room somewhere and watch the very first reconstructed pixels of an alien world slowly resolve into an image on a screen. And if the projections hold, if the funding continues, if the demonstration spacecraft currently being built succeeds in proving the solar sail technology, if phase after phase of careful engineering validation continues clearing the same rigorous bar the mission has cleared so far, then that moment is not a distant, abstract hypothetical belonging to some far future generation. It is a moment that could plausibly fall within the next 50 years, within a single human lifetime, beginning today. Think, for a moment, about what that actually means, sitting there in the dark tonight. Somewhere, right now, a young researcher is working through simulations of the Sun Diver maneuver, checking and rechecking trajectory calculations for a spacecraft that has not yet been built, aimed at a destination that has not yet been reached, carrying an instrument that has not yet been assembled, in service of a photograph that does not yet exist. And there is a real, non-trivial chance that within their own working career, that same researcher will watch that photograph slowly resolve into focus, line by line, continent by continent, and become, quietly, without any fanfare beyond the walls of a mission control room somewhere, the very first human being to look directly at the surface of a planet orbiting another star. It is worth pausing here and asking honestly what that moment would actually mean, beyond the raw scientific achievement itself, because the scientific value alone would already be extraordinary. Confirmed surface composition, confirmed atmospheric chemistry, mapped not just in aggregate but tied to specific geographic locations. Direct observation of weather patterns, of seasonal change, of whatever geological or biological processes happen to be unfolding on a world that has existed, silently, unobserved, for likely billions of years before anyone from Earth ever managed to look at it directly. But there is something underneath the pure science that reaches further than data alone ever could. Every human being who has ever lain outside on a clear night and looked upward has at some point asked some version of the same question. Is there anybody out there? It is one of the oldest questions our species has ever asked itself, older than written language, older than agriculture, embedded somewhere close to the core of what it means to be a creature capable of wonder in the first place. For the entirety of human history, that question has remained fundamentally unanswerable, not because nobody was clever enough to ask it properly, but because the tools required to actually answer it did not yet exist. This mission represents, for the first time in the entire span of human civilization, a serious, funded, physically grounded attempt to finally close that gap. Not to guess. Not to infer indirectly through the faint wobble of a star. To look directly and see what is actually there. And whatever the answer turns out to be, whichever of the priority targets is eventually imaged first, whatever the picture actually reveals once the reconstruction is finally complete, the moment that first image exists will mark a permanent, irreversible shift in how our species understands its own place in the universe. If the image reveals a barren, lifeless world, rock and dust and nothing more, that in itself would be a profound discovery, a genuine data point in the ongoing question of just how common or rare life actually is among the stars. And if the image reveals something else, oceans, forests, weather, or, however improbable, something built, something geometric, something unmistakably artificial, then the question that has quietly haunted our species since the very first person looked up into a dark sky and wondered, would finally, after everything, have an answer. Lying here tonight, it is worth simply sitting with the strangeness of the timing. You happen to be alive during precisely the decades when this became possible. Not merely theoretically possible, in the way Einstein and Eschleman first sketched it out decades ago in papers most people never read, but practically, physically, financially possible, moving through real funding phases, real engineering validation. A real demonstration spacecraft scheduled to fly within the next couple of years. The gap between wondering and knowing, a gap that has stretched across the entire history of human civilization without ever fully closing, may finally close within your own lifetime, or very close to the edge of it. And whether or not you personally live to see the final image, the fact that it is even possible, that the physics holds together, that the engineering keeps clearing every bar set in front of it, that somewhere a small dedicated team is patiently working toward exactly this outcome, is itself something worth carrying quietly with you as you drift off tonight. Part 12. What the light has been carrying the whole time. Let the story settle now, the way it always does toward the end of these long, quiet nights, back down from galaxies and black holes and $40 billion mission architectures, back down to something simpler and stranger and somehow more comforting than any of the numbers we have spent the last 2 hours moving through. Here is the thought worth carrying with you into sleep tonight. Every planet capable of hosting this kind of image, every world on that priority list, every rocky, temperate, potentially habitable world scattered across the galaxy that we have not yet found and cannot yet name, has been sitting there this entire time, quietly emitting and reflecting light in every direction for as long as it has existed, billions of years in most cases, long before human beings existed to wonder about it, long before there was anyone anywhere capable of asking whether anybody else was out there. That light has been travelling outward the entire time, unbothered, unwatched, some tiny fraction of it happening to pass close enough to our own sun to be bent gently by the curvature of space itself and sent onward toward a single, narrow, invisible line stretching out into the darkness past the edge of everything humanity has ever physically touched. Waiting, not for anything, simply existing the way light does, indifferent to whether anyone would ever arrive to gather it. That is, in the end, the quietly strange thing about this entire idea. We are not proposing to build something the universe does not already contain. We are not inventing a new kind of physics or discovering some previously unknown force. We are simply proposing finally, after a century of the idea sitting patiently in academic papers that almost nobody read, to go and stand in the one specific place where an answer has been waiting the entire time, gathered and focused and magnified by gravity, for anyone patient enough and clever enough and simply willing enough to make the journey. Einstein believed no one ever would. He said so plainly, almost dismissively, in a paper he only reluctantly agreed to publish, convinced that the alignments required were simply too rare, too demanding, too far beyond anything a civilization could realistically achieve to ever actually matter, and for most of the 20th century he appeared to be right. The idea sat quietly on the margins of physics, cited occasionally, discussed in passing, waiting for a century's worth of advances in materials science, in propulsion, in computing, in patient, careful mission engineering, to finally catch up to what the mathematics had been quietly promising the entire time. It has, or very nearly has. A demonstration spacecraft, testing the exact solar sail technology this entire mission depends on, is scheduled to fly within the next couple of years. A research team has cleared 3 separate phases of one of NASA's most demanding evaluation programs. Each phase harder than the last, each one requiring them to prove, a little more rigorously each time, that this idea is not simply beautiful, but achievable. And somewhere, quietly, patiently, a small group of scientists continues refining trajectories and testing materials and running simulations, building piece by piece toward a very specific, very personal goal, to stand in a room somewhere, 20 years from now, and watch an image slowly resolve into focus on a screen, and know, for the first time in the entire history of anyone who has ever lived, exactly what another world actually looks like. Whatever that image eventually shows, whether it reveals a quiet, barren world of rock and ice, or oceans catching starlight along coastlines no human eye has ever traced, or something else entirely, something unmistakably built, arranged in patterns no storm or river or mountain range could ever produce on its own, the moment it arrives will belong to a very small number of people standing in a control room somewhere, watching pixels assemble themselves out of a century-old idea that almost nobody believed would ever actually work. And somewhere far above you tonight, invisible, unnoticed, entirely indifferent to whether anyone is listening, our own sun continues doing exactly what it has always done. Burning quietly, bending the space around it exactly as it always has, exactly as it always will, focusing a thin, invisible corridor of light out toward a point 550 times farther than the distance between you and it. A doorway that has been standing open this entire time, waiting for nothing in particular, asking nothing of anyone. Simply there, the way it has been there for billions of years before you existed and will likely still be there, quietly bending starlight long after you are gone, patient in a way only a star can afford to be, holding open a door that someone, eventually, is finally getting ready to walk through. So if you find yourself outside some quiet night, looking up the way you did as a child, remember that the sky is no longer only a place to wonder about. It has become, slowly and patiently, a place we are actually learning to see. Somewhere out past the edge of everything we have ever touched, a thin corridor of bent starlight is waiting, doing nothing, asking nothing. Simply holding a door open until someone finally walks through it. Maybe that happens in your lifetime. Maybe you are the one lying here tonight who gets to watch that first image resolve, pixel by pixel, into another world. If tonight gave your mind somewhere gentle to drift, consider subscribing to the Sleepless Curiosity and turn on notifications so you never miss the nights we spend like this together. Leave a like if you made it this far and tell me in the comments where in the world you're falling asleep tonight. Rest well. The universe isn't going anywhere.